Hello to all. This is Naren from School of Chemical and Biotechnology, SASTRA University. This is a short lecture as part of the Chemical Engineering Thermodynamics 2 course. We are in lecture 15 part 3, and in this lecture we are going to see the criteria for a chemical reaction equilibrium. So let us write a generic reaction scheme. So a generic reaction scheme for a reversible reaction. Let's assume that A moles of A plus B moles of B are reacting to give C moles of C and D moles of D in a system. So you have a system. So this is a single phase system with pressure and temperature known. So there are A, B species, like say there are B species, there will be species of D, everything. So there are species in this system and they are reacting as per the scheme wherein A moles of A reacts with B moles of B and C moles of D and D moles of D. For we can also number this system as 1, 2, 3, 4 for ways of simplicity of equations. So let us number this as 1, 2, 3, 4. So that means N1, N2, N3 and N4 denotes moles of species I, in this case with this respectively A, B, C, D, right? And what are these A, B, C, small a, small b, small c and small d? These are the stoichiometric coefficients. So like for example, the stoichiometric coefficient of the species A is actually minus a. The stoichiometric coefficient of the second species, which is of the species B, is minus b. The stoichiometric coefficient of C, which is the third species, is plus c. Stoichiometric coefficient of D, which is the fourth species, is plus d. So this denotes the stoichiometric coefficient, and remember it's a signed stoichiometric coefficient, so that means it has negative sign for the reactant species and it's a positive sign for the product species. So this is what we have seen in the last lecture, and just a quick recap of that. Now we have also seen by mole balance that when you have the reaction scheme like this, we know that dNA by minus A will be equal to dNB by minus B equal to dNC by plus C equal to dND by plus D, which is in general then for any species dNi by mu I is equal to epsilon. This epsilon is called the extent of reaction, right? This is also called, there is an alternative name for epsilon, this is also called as reaction coordinate. So this is also called as reaction coordinate. So now if you see this particular relationship, that means we have for any species which is reacting, so we are only considering the reacting species, and we are assuming the system also has only the reacting species. So it's a single phase system and the system has only reacting species. So that is what we are considering at this stage. So it's a single phase system. Within the single phase system, we will first apply to a vapor phase, and then we will see in the subsequent lecture what will happen if it is a good liquid phase, and considering only the reacting species. So that means there are no inners. We will see later on what will happen if we have inners in the system, but at the beginning we are just focusing on these two. So dNi by mu I is equal to epsilon. There is no I over here, so please remember this is incorrect. This also we have seen in the last lecture, because this extent of reaction is same for all the species. So that means dNi on rearranging will give mu I into epsilon. So this is the relation that we get from the balance, the mass balance, or what we call the mole balance for the reaction. Now let's go back to the system. So we have a system okay, at a temperature and pressure. Then there are species which is reacting. So what about the Gibbs energy change in the system? What about the Gibbs energy in this system? So we know that the change in the Gibbs energy of the system, so the change in the Gibbs energy of the system is because of the change in the pressure, or could be because of the change in the temperature, or because of the species that makes up the system. So we can say that this is because of the change in the pressure of the system plus the change in the temperature of the system, or because of the third component that we know as because of the change in the Gibbs energy, because of the change in the composition of the system. And because we have number of species, this has to be summed up for every species from 1 to n. This I goes from 1 to n. Now obviously these are measured at constant temperature and keeping n constant. Here P is an Nn constant, and this is at Pt, and the moles of all other species other than this is held constant. Now if you recollect, this is what we write it as the chemical potential or the partial molar Gibbs energy. So that means the change of Gibbs energy in this system can be written as dou G by dou P into Gp, and just not writing this bar, but it is understood dou Gt by dou T dt plus sigma mu I dni. So this is what we know it. Now in this case, if we apply what about at constant temperature and pressure, because we have already said it's a reacting system, but the temperature and pressure is fixed. So if the temperature and pressure is fixed, we know that these two terms goes to 0 because this is not changing and this is not changing. So which essentially means that dgt is equal to sigma mu I dni, right? So we know that it is sigma mu I dni. Now this dni can be replaced in terms of the mole balance that we know. So if you use this expression, in this mole balance, the expression from the mole balance in the expression for the Gibbs energy change, we get it as this is equal to sigma mu I epsilon into, sorry, this is what is dni. So just let me write it before, let me use the stoichiometric coefficient to be multiplied with this partial molar Gibbs energy, and let me rephrase it as mu I and the extent of the reaction. This is equal to dgt. Yeah, so what we have seen is in a system with a reacting species at a given temperature and pressure, where the pressure and temperature is constant, we will see that dgt is given as sigma mu I. This is partial molar property, partial molar Gibbs energy. This is the stoichiometric coefficient, and this is the extent of the reaction. Now, at equilibrium, what happens at equilibrium? Now, when an equilibrium is attained, you know that G is minimized. So, the Gibbs energy is minimized. So, that means in a plot of G versus extent of reaction, you know that that is the point of minimum Gibbs energy for the system. This point of minimum Gibbs energy of the system remains invariant with respect to temperature and pressure. So that means this is at a given temperature and pressure. With respect to the reaction, the system attains that particular point where the energy, Gibbs energy, is minimized. So that means any change in Gibbs energy is 0 at equilibrium. So at equilibrium, given a temperature and pressure. So now if you use this condition, over here. So you will get dgt equal to sigma mu I. This is extent of reaction. Now this is equal to 0. So now you have choice. So of these three variables, so it's the product of these three variables summed up, and that should be equal to 0. Now let's think whether this is the first case. We can say that the extent of reaction epsilon itself is 0. This is a very trivial solution. So that means if the extent of reaction itself is 0, which means there is no reaction in the system. So that means if there is no reaction in the system, it could be like everything is inert, or the reaction itself is not proceeding given the reactive species. But this is not unacceptable, because we have already started that we have a system with the reacting species and the equilibrium is attained for a given scheme. So the scheme which is given eventually as AA plus BB reacting with CC and DD. So that means this trivial solution is not acceptable. The second trivial solution one can think of is all the stoichiometric coefficient being to 0. This is again is very trivial, and this is not acceptable in a reaction scheme. So we cannot have all the stoichiometries being 0 and then we say that there is a system. So that means these two are just mathematical possibilities but not physically acceptable. Now you can have a third possibility where you can say this is again a trivial mathematical trivial solution, where you can say that the partial molar Gibbs energy or the chemical potential of all the species are 0. So this is again a very trivial solution or a very obvious mathematical solution, but again does not make a physical significance. So that means all these are ruled out. So these are not acceptable. Now what one can think of is then obviously the fourth case. So that means we are going to have a finite value for the extent of reaction, and the only other way this summation could become 0 is that the sum of these two entries could become 0, because you know that this is going to be constant for all the species involved. So essentially, which means we can write this equation or this expression as sigma times, so this is extent of reaction sigma times summation of mu I into the chemical potential of this system. So if you take this as product of two quantities, this is a finite quantity. So the only case is this has to be now 0 to make sure this product of these two terms becomes 0. Now how we took this term out, because this is constant for all the components, so there is no component index over here. For every component that takes place in the reaction, we know that this is constant. So for all the components, this is going to be the same value. So going by this, the criteria, we arrive at the criteria for a single phase reactive system at a given temperature and pressure to attain chemical equilibrium is given by summation of the signed stoichiometric coefficient times the chemical potential of this of all the components. The reactor component should be equal to 0, which means which can also be written as sigma, the signed stoichiometric coefficient, divided by the partial molar property of all the component is equal to 0. So that means if you ask to expand, so this is as if for a reaction like AA plus BB, reversibly going to CC plus DD, this amounts to mu A of G A bar plus mu B of GB bar plus mu C of GC bar plus mu D of GD bar. This summation should be equal to 0. So here we come to the end of this lecture, and in the next lecture we will see how to get a workable expression for this criteria. So I'll just quickly write in a bullet point what we have seen in this lecture. So what we saw, so we just recapitulated that dni by mu I is equal to extent of the reaction, and which is constant, and using this with respect to the change in Gibbs energy of a system, we arrived at the criteria for chemical reaction equilibrium as mu I into the chemical potential of all the system, which can also be written as mu I into Gi bar is equal to 0. So this is the criteria for reaction equilibrium, okay, at a given temperature and pressure. Thank you all for watching this video.